Lisa Randall is here. That's Dr. Lisa Randall. She is a professor of theoretical physics at Harvard. She has done groundbreaking work into the existence of multiple extra dimensions. More about that later. Her theory, which she developed with her colleague Raman Sundram, has been called the best scientific idea of the last decade. She is now the most cited scientist in all of physics. It is a pleasure to have her at this table for the first time. Welcome.
Thank you. It's a pleasure to be here.
Now, John F. Kennedy once had Pablo Casals at the White House at the invitation of the First Lady. And he said to her and everyone concerned, I don't really know the music of Pablo Casals and much about him. I just know he belongs at the White House. So I'm saying to you, I don't know much about physics. I just know that I'm interested in science and you belong here at the table because you're doing stuff that, if in fact it's right, as some of your colleagues have said, will change everything. You know, let me start about physics. I thought we lived in the world of molecular biology and brain science, and that sort of physics was old hat stuff. That goes back to Albert Einstein and nuclear technology and understanding E equal mc squared and all of that. That physics was a dead science.
Well, physics certainly does have a long history, and it is true there are some fields that are really just emerging.
Right.
But the thing is, with Einstein developing E equals mc squared and his theory of general relativity, what he developed was an entire toolbox that told us if you have various objects in space, what does space look like? How does the universe evolve? I mean, cosmology has turned into a science since the time of Einstein. I mean, before that, people had ideas about the universe, and you'll often see people refer back to the same notions that occurred earlier. But really, it's now a scientific theory. You can say, I have this distribution of matter and energy, this is what happens. There are experimental tools to explore cosmology that weren't there before. There are experimental tools to explore physics of elementary particles and very short distances that haven't been there before. So it's true, there were tremendous breakthroughs in the last century, but we're building on those breakthroughs.
Is cosmology what you're interested in?
I do an overlap area. I do particle physics,
right.
Theoretical particle physics.
I always assumed they were the smart guys. And I mean that without gender reference.
Should I question the smart or the guy's part? But if you know what the universe is made of, that's going to tell you how, to some extent, how it evolves. And if you know how it evolves, that gives you constraints on what it's made of. So it's not like there's one field of physics and you can do it in complete isolation from another one. I mean, part of what makes the field rich and enjoyable for me is that you can ask questions not just about elementary particles, but also about cosmology. And when you begin to think about ideas about the whole global nature of space-time, you can't help but think about cosmology as well.
I want to do this. You were born in Queens, went to Harvard, got a bachelor's degree, then or master of science or something, and then got a PhD from Harvard, right? Mm-hmm. Then you went to MIT. Then you went, or
I actually was a postdoc in Berkeley.
And then Berkeley, then MIT, and then to Princeton, and then you came back to Harvard. Mm-hmm. You're now doing extraordinary. You're writing a book called Warp Passages: Unraveling the Mysteries of the Universe's Hidden Dimensions. I love three words there. One, unraveling the mysteries, and secondly, hidden dimensions. What are you trying to find out? What is it you want to tell us that we're going to be amazed by if it proves right?
We're really trying to understand what, it sounds very vague, but what is the fundamental nature of matter? And forces. What are the fundamental forces, and why are they related in the way they are? So we're trying to understand more about gravity, for example. Why is gravity so much weaker than all the other elementary forces we know about? That is to say, the three other elementary forces we know about, electromagnetism,
right,
and weak and strong nuclear forces. Gravity is far weaker. I mean, if you think about it, you can pick up a paperclip with a tiny magnet competing against the entire Earth. And the fact that you can jump up and down, I mean, gravity is not a strong force. Although it dominates things, it's only because there's big, massive objects.
It's not a strong force where we are and might be a strong force somewhere else?
Yeah, so there's a question of how it manifests itself. And if there's a big, energetic object, it seems strong. But if you took two elementary particles and compared the force of electromagnetism and the force of gravity, right, I mean, gravity is negligible. You don't even have to consider it. You throw it away. But why is that? Why is gravity so much weaker? And for particle physicists, it's even more mysterious than just why is it so much weaker. If you naively just sat down and calculated how you expect the forces to be related, you would think that those forces should be about the same strength. So there's a big question that particle physicists have is, why is gravity so much weaker than the other forces?
Yeah, why do we think so?
Well, we think so because we can measure it.
No, but why is it, is my question.
Exactly.
What are the possible, that we can understand? Possible explanations?
Well, so that's a question people have been looking at since the 1970s, and it's what's led me into thinking about ideas like extra dimensions of space, which we can talk about.
Right. We won't get that in a moment.
But we won't get there right away. But it really is a very puzzling question, and it really seems like something dramatic would be needed, like a new symmetry of space-time or extra dimensions of space. It's a really big thing. It seems a very concrete question, but it could lead into really radically different notions of what the space-time we live in is. And so that's one question we have. But we have other questions, too. What is the fundamental nature of gravity? Ultimately, we do want to know what's a quantum theory of gravity that combines it with quantum mechanics. We want to understand what the universe is made of. What is the dark matter? What is the dark energy that's not carried by matter? So there are some pretty big questions that are driving us.
Okay. This multiple dimensions idea. Now, we know that, I think even Einstein said this, there were 4 dimensions, correct?
He included time as a dimension. That was actually a radical new way of thinking about things at the time.
So it's, what are the 4 dimensions?
The 3 spatial dimensions that we know about: left, right, forward, backward, up, down, and time.
And then string theorists came along and said there are 10 dimensions.
Yeah, string theorists seem to think that there are at least 10 dimensions.
And how many do you think there are?
I like to leave it an open question. I like to say, what have we measured? What do we know? And could there be other dimensions out there? And there certainly could be other dimensions out there. It might be 10 or 11 space-time dimensions, as string theorists tell us now. But it's really, ultimately, I hope there's going to be some experimental input to this and some theoretical input to let us know, is it really true that what we see is all that's there? Or is it a case where we're just not physiologically designed to experience or see those dimensions, but we'll eventually find evidence of them?
What's likely to be another dimension?
What do you mean by that?
Well, I mean, there are 4 dimensions. What would be a 5th? Or what would be a 6th? Or what would be...
The other dimension...
I'm trying to figure out what a dimension is. I can understand space and I can understand time.
Right.
But I can't understand what might be next.
That's right. And one of the things that makes it really hard to think about extra dimensions is that we can't picture them. I mean, in my book I say, a word is worth 1,000 pictures when it comes to extra dimensions, because we can't picture them. But one really clever idea was, Edwin A. Abbott wrote a book called Flatland.
Right.
And he said, to think about, we can't picture, we think we live in 3 dimensions. Maybe there's a 4th or even more spatial dimensions out there. He said, that would be the same situation as if you lived in a 2-dimensional universe, or creatures lived in a 2-dimensional universe and couldn't perceive a 3rd dimension. What would the 3rd dimension be for them? I mean, they would be as puzzled asking that question as we are asking, what is this 5th dimension of space-time? So suppose you had creatures living in 2 dimension. What would a 3rd dimension look like for them? Well, they're not going out there, but maybe they'd see an object come through. So maybe they'd see a 3-dimensional object, like a sphere, pass through their universe. Yeah. And if they did that, they would never see the sphere in its entirety, but they would see evidence of the sphere. They'd see a series of disks that grew in size and then decreased in size and then disappeared as the sphere passed through. In the same way, we could imagine a hypersphere, a 4-dimensional sphere, could pass through our universe, looking like a series of spheres that grow in size and then decrease in size. I mean, the fact is that we can't picture these dimensions, but they could be there, and energy could be transferred to those dimensions. Particles could travel in those dimensions. Gravity could spread throughout that dimension. The fact that you can't picture it doesn't mean that you can't imagine it, and there are ways to picture cross-sections or projections or slices. But really, to picture it in its entirety is challenging for everyone. But it doesn't mean that we can't mathematically derive the consequences of what would happen if these dimensions were there.
Now it's time for show and tell.
I was sort of using the show and tell there.
I know you were. Show me the first picture and the second picture. We have it for the audience at home. If you can just pick it up and identify which number it is. So, like number 1 would be a good place to start.
Here we have a hose that's stretched across a football field.
Right.
So suppose we had a hose that was stretched across a football field. Well, that looks fairly one-dimensional in the sense that you think that there's one dimension that you can go along. Right. But of course, if you were standing on the field and picked up the hose, you would see that its surface was 2-dimensional, its interior is 3-dimensional. And although this sounds so obvious, it's really an important way of thinking in physics. The fact is, you only care about the scales that you can actually resolve things, the scales where you can make measurements. Because the idea of extra dimensions has been around for a long time. I mean, Abbott wrote his book in the late 19th century. Right. And Einstein completed his theory of relativity in 1915, general relativity. And only a few years later, somebody named Theodor Kaluza proposed the idea of an extra dimension. So why is it that physicists today are really thinking about extra dimensions? Well, one of the reasons is that we think it might actually have something to do with our universe. I mean, that's, I think, for me, the most important reason. But another reason is, in fact, string theory. And it's introduced the idea that maybe those dimensions really are there because that's the only way the theory makes sense. But string theory has also introduced something else. In the 1990s, the physicist Joel Polchinski realized that there were these other objects in the context of string theory called branes. They're named branes now.
Yeah. B-R-A-N-E-S.
Thank you for clarifying. That word is sort of related to membrane. Yes. And the idea is that there could be, even if you have higher dimensions, even if you have a fifth spatial dimension or a fourth spatial dimension out there, there could be objects in the universe called branes that don't spread throughout the entire universe. And maybe stuff is stuck on those lower dimensional surfaces. So here we have an analogy, just to give you the general idea. I mean, you might have a three-dimensional room that's
that
figure
would be
5. That's figure 5.
Right.
You might have a three-dimensional room, but in that room there might be a shower curtain.
Right.
And on that curtain there could be water droplets.
Right.
And those water droplets are only on the two-dimensional surface of the curtain. They're not going out throughout the three-dimensional room. They're really stuck there.
Right.
And in the same way, referring to figure 7, right, it could be that we and the stuff of which we're made in figure 7,
right,
we and the stuff of which we're made could really be stuck to a brane. So this brane, although it's drawn as two-dimensional, think of it as a three-dimensional surface. So if you have this three-dimensional brane and the stuff was stuck there, it would look just as if the universe was three-dimensional. If everything, if for example, photons and electromagnetism could only travel in the three dimensions of the brane, well, that would explain why things look like they're three-dimensional. After all, light doesn't get outside the brane. So it could be that some of it is actually still stuck in 3 dimensions, even though another dimension is out there. What makes it interesting, though, from the point of view of a physicist, I mean, if everything was stuck in the 3 dimensions of a brane, who cares that there are other dimensions? Right. We'd never interact with them. But it is always true that gravity goes out into those dimensions. And so the squiggly lines that in that figure represent the fact that gravity always interacts with the other dimensions. Gravity will never be stuck on this brane. And that's what's so interesting. With these branes, you can get the geometry of space-time. We're used to thinking, we physicists at least, are used to thinking of space as the same everywhere. As far as we know, the laws of physics are the same throughout the 3-dimensional universe. But it could be that in these extra dimensions, because of the existence of these branes and energy throughout the universe, space-time can be warped. I mean, even in our universe, it's warped to some extent. I mean, that's why there's interest in cosmology. But with this other dimension, it could be very dramatically warped. And it's that can really explain properties of gravity that we see in our universe, because gravity is spreading out in those dimensions. And so it could be that gravity isn't just spreading out evenly everywhere. It could be highly concentrated, for example, in the region of a brane. And that's one idea that we got very excited about.
Okay, continue on, because I like these.
Okay, continue. Excellent.
Yeah.
Okay, so
yes, exactly.
We will now refer to figure 11.
All right, let's go to that one. That shows the 2 branes and illustrates a weakening of gravity access.
Yeah, so 11 to 10 is illustrating this weakening of gravity. Yeah. That's right. So you can imagine not just one brane, but 2 branes, and we have our little brane world figure to say that there's one brane called the gravity brane,
right,
and there's another called the weak brane. And the reason they're named that is because it turns out, and this is something that Raman and I discovered quite to our amazement, we just solved Einstein's equations of general relativity. We solved the equations that tell you what gravity is like in the presence of these branes and the energy that we assumed. And we found that space-time is dramatically warped. So all we had was 2 branes bounding a 5th dimension. So this is the end of the universe, this is the end of the universe. And so we had this, and we solved and asked, what does gravity look like? Now, if there were no energy, then gravity would just be spread evenly everywhere. But because of the energy, it turns out, as is illustrated in figure 10, gravity is getting concentrated in a region of one of the branes, the gravity brane.
Right.
And this is really, it just followed from the equations. But what it means is that if you live anywhere except at the gravity brane, where gravity is concentrated, you would naturally see gravity as very weak. And so this, again, was this enormous puzzle. But it turns out gravity sort of decreases exponentially quickly as you go away from that brane. So if you live on this weak brane, and this is what we're wondering if it's true, could there be an extra dimension? And could it be that gravity is highly concentrated somewhere else? So that where we live, gravity is
concentrated
weak.
Where the extra dimension is?
It could be concentrated out in the extra dimension on this other brane called the gravity brane, for example, or just somewhere else. If gravity could be concentrated away from us, if where we live, gravity could be very weak. And this might sound like a really exotic theory in the sense, which it is, but it actually has measurable consequences, which makes it worth studying as a physicist. So it could be that the reason we perceive gravity as so weak is because gravity is concentrated elsewhere in an extra dimension, and we're in some sense just getting the tail end of gravity. If you look at figure 8, it's a very loose way of saying another interpretation of what's going on, which is that space-time is warped. I mean, that's where the title of my book came from.
Right.
And it's so warped. How do you think about this warped space-time? Well, one way of thinking about it is that gravity changes in the extra dimension. But another way of thinking of it is that you actually rescale things as you go out in the extra dimension. So although you might have thought everything is heavy, that's only true at the gravity brane. By the time you get to the weak brane, things are light. And so that gravity looks weak because things are light there. And that could be another way of interpreting the meaning of warped space-time and why it can affect this kind of measurement. And see, as particle physicists, if there are only 3 dimensions, we really think that the masses should turn out to be about the same. And that's what our theory tells us. I mean, it's really an embarrassment because the standard model of particle physics, which describes the most basic elements of matter and the forces by which they interact, it works perfectly. But it's based on a big fudge because we don't know why there are these very different mass scales, why gravity is so much weaker than the other forces that we can ignore it. So until we answer that question, we don't have the ultimate answers. I mean, we think the standard model is right, but what is it that underlies the standard model? So could it be that particle physics needs to be embedded in some more complicated theory? But it could be that the way we've been thinking about space is wrong and that actually there are extra dimensions and that we are living in a region where gravity is weak. And here's an example where that might happen.
Well, that would be great, wouldn't it?
I think it would be great. It would be very exciting. And what's really exciting, too, is that if it is true, you can actually, at this accelerator we talked about earlier, the Large Hadron Collider, if it's right, because particles are light on the weak brane where we live, you could actually see particles that travel in extra dimensions. They could actually detect. Because E equals mc squared, by having high energy, they can produce particles with big mass m, so heavy particles. And that means that this high energy accelerator, you have the possibility of producing particles that are heavier because they travel in extra dimensions. So you can measure their properties. In the warped space-time, you can actually see what these particles look like and see whether this idea is right.
Who's most interested in your results?
Among the physics community?
No, generally. I mean, is government interested in this? I mean, do they think that there's some way this can be used to? I
think we all are resigned to the fact that, first of all, we'll be lucky if we even...
Physicists?
We all physicists. First of all, we'll be lucky to reach the energies where we can detect it.
Lucky? So you might not ever be able to detect it? Well,
I mean, we want to build high-energy accelerators. It could be that we need to get to a little bit higher energy to learn more. But right now, we think we will definitely learn something at the energies that we will explore. But there could be even more exotic phenomena like higher dimensional.
It's a really incremental step.
It's not incremental in the sense that it's 7 times the energy of current accelerators. So it really is the right energy to probe these questions. It's just that if you get a little bit more energy, you might learn a little more. For example, if you get to even higher energies, you might be able to make higher dimensional black holes if this idea is right. So there are new things that could occur with higher energy. But we do expect to be able to know the answers to these questions from the Large Hadron Collider. I just want to clarify.
Go ahead.
But the thing is that, with physics, it's always, you're sort of at the edge. You just can barely measure something. And of course, no one can anticipate, is it useful? And probably it won't be. But, they would have said the same thing about electromagnetism or when Einstein did general relativity. Who knew that it would be used in GPS systems?
Yeah, exactly.
So to ask us, at this
Thank
point.
God.
But on top of that, there's just this general way people get excited about science and the world. It's not just these concrete applications. It kind of just drives people being interested in things and learning how to do science and learning how to think in these ways.
Well, Nobel Prize winner Jerome Friedman, your former colleague at MIT, I think said that if we see evidence of what has been proposed by you, it will be extraordinary. It will shake up everything. It's pretty good.
That would be pretty good. It's true. If we know that we live in a universe with more dimensions, of course, you can't ignore that. You can't ignore that for any of the types of science we do. It would tell string theorists this is the kind of thing they should be trying to find in their theory. It would be telling cosmologists that you have to take extra dimensions into account when the universe evolves.
Are we months, years away from understanding the next dimensions?
That's a really great question. It turns out that there will be an accelerator So an particle accelerator accelerates protons to enormously high energy. And there's going to be a new one that turns on. It turns on in 2007, but really will begin operation in 2008. It's called the Large Hadron Collider, the LHC. It's going to be at an accelerator facility called CERN near Geneva. And that will answer this question about the weakness of gravity. It will also answer questions about
whoever
how
has the
particles
machine
acquire
gets
mass.
the prize?
No, there's thousands of people working on this experiment. And so one thing they want to, people often have a misconception about how these accelerator experiments work. They think it's kind of like telescope time, that different people ask for time. There's a lot of people who are going to be collecting data. And once they have that data, what happens when you collide together these protons at enormously high energy? There will be people who try to piece out from it what were the different, they'll test the different ideas. So lots of people have suggested what might be there. But generally they're going to look for energetic particles. They're going to see where did they come from, what could have been, what was producing whatever they found. So it's going to be a long process where this data gets analyzed. So it's not like everyone is lined up racing to do it, but once the data starts coming out, people are going to want to be interpreting it in different ways, and we're going to see which it corresponds to. Does it correspond to ideas as exotic as extra dimensions?
What do you think that you can't prove?
What do I think that I can't prove? There are a lot of things, and proof for a physicist is a little different than proof for a mathematician or a logician. I mean, there's proof in terms of the internal consistency of our theory and all the math working, but there's proof in terms of other people going out and doing experiments and verifying that these ideas you have, your initial. So we're making assumptions. I'm saying there might be extra dimensions. There might be objects in these extra dimensions. And I can self-consistently derive what the consequences are. But the question is that initial assumption right? So I can't prove that. Someone has to go out and actually measure that and see, is there evidence
we have new tools to do that?
We have tools to do that, but you do have to combine it with theory, because it's very hard to just go out and measure these dimensions. For whatever reason, they're very well hidden. So it's in conjunction with saying, if the extra dimensions affect our universe in this way, this is the experimental evidence you will see. That's the kind of thing that we want. That would be the kind of proof we would find.
What drew you to this? I mean, how did Lisa Randall from Queens, with all these fancy degrees and all these cheerleaders, I mean, was it math? Was it precision? Was it science was a way to be, was about asking questions and finding answers? What?
You know, it's funny, because it really was an evolution. You know, I grew up in New York. You know, there was a lot of upheaval at the time I was growing up. And I think I really did like the fact that if you did a math problem, it had an answer. It wasn't a question of what the teacher said they thought the answer was. I really liked the fact that there was this definite answer. So I was, I mean, I liked a lot of subjects. I liked school. But
school liked you, I think.
we got along well.
Got along.
But I really did like doing math and science, but math especially at first. And then I actually didn't do physics till I was in high school. I actually went to Stuyvesant High School here in New York, and I began to like physics, and it began to seem like physics was a possible career. I mean, it still seemed very strange. I mean, no one in my family was in academia.
Did you know any physics? Any physician? I mean, any physicists?
I didn't know any physicists, no. I mean,
didn't know any?
No, I didn't really know any scientists, actually. Yeah. So it seemed a bizarre thing to be doing, I have to admit.
You had no role model?
I guess I didn't really have role models at that time, no. So then, you know, I remember, yeah, it's true. I remember because I had a freshman roommate whose parents were professors, and I was a little bit jealous because I thought, you know, she feels more comfortable in an academic environment than I ever will. But she seemed uncomfortable with it too, so I didn't feel too bad. But it was true that it was just the science itself that sort of got me into it. It wasn't necessarily the life of a professor, but really, I really just liked doing science. And I didn't start off thinking I would work on extra dimensions of space, that's for sure. Yeah. I mean, it would have seemed probably the same way it seems to you, like a little bit like science fiction. And it really was the fact that it was the science that drove us to it. I mean, we didn't immediately say, let's just look at this wacky theory of extra dimensions. We really tried different ideas. And when I say we, I mean the entire scientific community since the 1970s has been trying to solve this puzzle of the weakness of gravity. And there really aren't any completely compelling solutions. So it made sense, especially since string theory tells you maybe there are these extra dimensions. It also introduced some new ideas. So it made sense to explore what could be the consequences if that was true.
As there frequently is in science, is there some great competition? There's you and 3 or 4 other people who are competing, knowing that whoever unravels this
Yeah.
Wins the prize.
It's funny.
And you know what prize I'm talking about.
Oh, well, I don't know. I didn't even think about that prize.
No, I know you shouldn't. But you know what I mean. I mean, this sounds so
it's funny because
extraordinary when we think about it, because it's the way the world is, or might be.
We're sort of working together and in competition at the same time. People build on each other's ideas, and
you share them,
and we do share them.
And you report them in journals.
And
science.
not only do we have them in journals, when you finish a paper, you post it on the web immediately, so people see your results the next day. So it really is shared, and so there's some ways in which you certainly want to get the idea out there first, especially if you've had this great idea. But there's another part that's like, well, if someone else is going to have that idea, might as well work on something else. You sort of want to have these ideas that are really unique. So it's a combination, and I think that it's productive that way.
You went to school with Brian Greene, did you not?
I did. We were actually in the same class.
And how much do you agree on, and how much do you disagree on?
I think we're both people that are open to the idea that we really love what we're working on, but it could turn out to be wrong. He works more strictly on string theory because he believes more faithfully on string theory.
Than you do.
I think I am a little bit more skeptical in the sense that I want to see, what is it good for? What can we solve with it? Could it explain phenomena in our universe? Right. Are there even testable aspects of the theory, or at least does it lead to some
do you have an operative theory?
Well, I mean, these ideas are using ideas that aren't necessarily associated with string theory, but are sort of motivated by string theory. Extra dimensions, this idea of brains came out of string theory. Some ideas that we have feed back into string theory to say maybe space-time really is warped, and if so, you could have infinite extra dimensions. We could be living in a pocket of 3 dimensions. So we're sort of we're all approaching the same problems, and we're sort of even using similar tools. But I think our approaches are slightly different. He'll derive things from string theory more, and I would try to build up more from saying, these are physical questions, can we solve them?
Do futurists and science fiction writers and filmmakers sort of beat a path to your door to say, what's going on out there so I can be ahead of the game?
I have had some people contact me about those things. Yeah, I mean, they do like to incorporate these notions. In some ways, I have to say, sometimes science is more exciting than fiction. I mean, some of these ideas, this idea of living in a pocket of 3 dimensions inside a higher dimensional universe, that's something that came out of the science. We weren't trying to find that. I mean, the equations gave that to us. So even this idea that there could be an infinite extra dimension of space because space-time was so warped, we weren't looking for that in the beginning. That came out of it. So I think there are some ideas that come out of just doing science that even of course, we could have sat down and imagined that, but it's really quite exciting. I mean, these aren't ideas that I had read in science fiction. I mean, they're really even more exciting. And the idea is to really just get people excited about. And I really did try to write a book where people could see what are the questions we're asking, how are we thinking about it. I didn't just try to say, we know the answers and here are the answers. I said, here is what we know. I mean, I try to say, we understand gravity to some extent. We understand quantum mechanics to some extent. We understand particle physics. Here are the remaining questions. This is what's driving research today. This is what we're excited about. And one of the things that's really rewarding for me is the number of people that write and say, I can't wait to see the results of the Large Hadron Collider. I mean, people, when people know what these questions are.
The questions you raise.
Exactly. When people know what these are subtle questions. They're not questions that I can just really explain. I mean, I can give some brief explanation. But to really understand them, you want to sort of understand what's behind it. What are these developments? I mean, as you said earlier, there have been hundreds of years of developments in physics. So you can't necessarily understand that just in three minutes. But you can understand it if you care and if you want to think about it and develop and see what is it. I mean, this is the edge of human knowledge. It's so exciting. And so I think for people to see that and have access to that is really worthwhile.
I frequently ask scientists, what is the one question you want to know?
I think one of the things that sort of you're getting at with the brain a little bit is just what can science do? How far can we get by doing science? Will there be answers to all these questions that we want to know the answer to? And can we access them with the brains that we have? And so they're sort of just the big questions. Then there are, of course, the questions of what is this universe in which we live? What is it made of? Does it have extra dimensions? Does it have other stuff? I mean, what
I was going to get to
there?
That other stuff. Does it have other people?
It does have other.
Is there something else out there? I mean, you're a scientist who's exploring these kind of things. I mean, does it lead you to believe that, damn it, it's not? We're just we're just a small part of something very big. Our universe, I mean by that, not our planet.
That's right. And I actually do think that that is true. I mean, sometimes some of these ideas are just so humbling in the sense of making you realize, I mean, one of the challenges, of course, to particle physics is how hard it is to reach the energies or the distances where you can study some of these ideas. There are so many things that can be happening beyond the scales that, not just the ones we see in daily life, but that we can even hope to detect at these points. So it really makes you realize that there could be what's sometimes known as a multiverse. There could be other universes out there that we really don't have access to. So we can think about them, we can do theory, but right now we don't know how to get access to them, and we might never. And it really is quite humbling. And so, for example, if we live in this brain...
we might never in our lifetime.
We might never in human lifetime. It's because, we live on a brain. Suppose it's true that we live on the brain. Well, then there, of course, could be other brains out there. There could be other brains. But suppose it was true that what we said earlier, that, say, electromagnetism and all particles and forces except gravity are stuck in our brain. That means if there's another brain, it would necessarily have entirely different chemistry. So all our intuition, based on the three forces we know about and the quarks and leptons of which we're made, would not apply there. It could be completely different stuff with completely different forces. There could be life there, but that life could be totally different. It could be the only force that we even have in common is gravity. I mean, that's a real possibility. So it really makes you realize just how limited what we have access to. Of course, understanding that part we have access to as well as possible is extremely worthwhile, but it does make you realize there could be a lot of stuff that's out there that we might never know about, at least experimentally.
What do you hope people get out of this? I mean, why should I read this book?
There's a number of things, and it really is geared towards different people.
I'm going to tell you, it's not easy, and you've tried to.
Yeah. And
or maybe it's not easy for me because I'm not that bright, but I mean,
No. I mean, the thing that isn't easy, and I know this, is that there's a lot of ideas in it, right? I mean, physics didn't develop overnight. There really are different ideas, and I had a choice. I could focus on just one,
right?
Or I can say this is why modern physics today is exciting, because it's a culmination of all these different ideas that are being brought together through some of the current research. And for me, that's what makes it exciting, the fact that you can pull in all these different threads and tie them together in what's happening today. And you don't have to understand all of them, but if you do, if you want to, I thought it should be there for people to understand. So the answer is it really depends who you are. I mean, there's some people that I think would want to just understand what is meant by the extra dimension of space. What do we mean by that?
Sure.
And that's what I'm doing in the first few chapters, just saying this is how to think about extra dimensions. There's some people that want to know what is the development of physics like, what is quantum mechanics, what is general relativity, and that's there too. But in addition to getting up to current research, I think it's just also this general way of thinking about the world. The idea of, we have this notion of an effective theory, the idea that you can have knowledge defined according to what you've measured so far, but that you can go beyond that. There could be something underlying it. And just how we can progress from understanding physics at certain distance scales and then understanding it at smaller and smaller scales. And sort of what are the questions we're addressing? How do we think about problems? What is it that... I mean, the other thing I guess I would like people to get is that it's not like it's all very rigid. I mean, there's some fluidity in the way we think about things, and there's some fun in the way we think about things. It's actually fun thinking about these big questions and trying to think how the world might work. And just a general sense of, what could be out there. So I guess there's a number of different things I'd like people to get out of it.
Warped Passages, Unraveling the Mysteries of the Universe, Hidden Dimensions. Lisa Randall, thank you for coming.
Thank you for having me.